that's not locked down. Zeros of a polynomial function. Zeros of a polynomial function is what we're looking at today. Use of the fundamental theorem of algebra to determine the number of zeros of a polynomial function. Find the rational zeros. Find the conjugate pairs of complex zeros. Find zeros of a polynomial function by factoring. And I think that's it, almost. Descartes' rule of signs. And find the zero of a polynomial function in real life. We won't do the real life, and hopefully we'll get to Descartes today. If not, we'll do it tomorrow. We'll split this across 2 days because we have today. So 2.5, 2.6, 2.7. We have 3 sections left, and then we are done with chapter 2. We have 3 sections left, and then we're done with chapter 2. The fundamental theorem of algebra. A lot of stuff. If f of x is a polynomial function of degree n, where n is greater than 0, then f has at least 1 0 in the complex number. Has at least 1 0 in the complex number system. Well, that's kind of odd, isn't it? Because that means for a function like, say, we've done this one before, haven't we? And we said x is equal to plus or minus 2. What does it say? Has at least 1 0 in the complex number system, yes? So we're saying x is equal to 2 and x is equal to negative 2. Is either one of these a complex number? Surprise, they both are. We can add 0i, because the I, we're very conceptually based, or conceptual thought is that a complex number is the term with I. We're very stuck on the fact that I is the complex number. It's not. A complex number is a plus bi. A plus bi, the real plus the imaginary. Any term with I is the imaginary part. The whole thing is a complex term. The real and the imaginary combine to make a complex term, make a complex number. So it's just not it's not just the I. We kind of get stuck on that every now and then, and we think about it. And again, when I was doing this and teaching this first time, I'm like, how do they do that? No, because we get kind of stuck on the thought that I, a term with I, 7i, 0i, is the complex number. No, it's the real plus the imaginary. Does that kind of make sense? Because again, it's easy to think that 0i is the complex term. It's easy to think that, but it's not. 2 plus 0i and negative 2 plus 0i, that whole thing is the complex term. Does that make more sense of what this is saying here? Yes? Now, we don't normally talk about it that way. We kind of talk about it more about the fundamental theorem of algebra, where whatever the degree is, the number of possible solutions, whatever it is. So if the degree is 5, we should have 5 solutions. Not unique, because we can have repeated terms. But we should have 5. Whatever the degree is how many solutions we should have. And that's helpful, because once we hit some of the other formulas, once we find 5 solutions for a 5th degree polynomial, we're done. We don't have to look anymore. Because how many solutions? So degree 5 should have 5. If I find 5, I am done. It's almost going along with the saying, it's in the last place I looked. Because if you find it, you stop looking. So hopefully it is in the last place you look. If it wasn't, like, why do you keep looking? Well, I found it 2 days ago. Why are you still looking? Moving on. The fundamental theorem of algebra, the linear factors. So a polynomial function has precisely n linear factors. The number of solutions. We can also write them as linear factors. And that works with complex or irrational. So if we have square roots, we can write them as linear factors. Because we can say that it is x minus 3. Because we've dealt with those. Those are linear factors. We've done those before, yes? We can also say x minus the square root of 2 and x plus the square root of 2, because we can have irrational. X minus 3i, x plus 3i, we can have complex. So we can have any of these here. And we can write them as linear factors. And we should always have the degree n where n is greater than 0 has exactly n factors. 1, 2, 3, 4, 5. This is degree 5 because we have 5 of them. That's all that's saying. Note that the fundamental theorem of algebra and the linear factor theorem tell you that the zeros or factors of the polynomial exist, not how to find them. Such theorems are called existence theorems. This is how many they are. We really don't how many they are or how we're going to find them, but this is how many there are. This is how many exist. First degree polynomial is this here. F of x equals x minus 1. Because the exponent that is not written there for x is 1. It has an exponent of 1. We just don't write it in. Because it's x to the 1 first power minus 2. This is degree 1. By counting multiplicity, the second degree polynomial function, this here, we have this. X squared minus 6x plus 9. And this here would be a third degree because the degree is 3. And that's it. Because we're just looking at the degree. That's how many they have. The rational zero test relates the possible rational zeros of a polynomial function to the leading coefficient and to the constant terms of the polynomial function. Rational zeros is p over q. We do plus or minus p over q, where p are the factors of a naught, and q is the factors of the leading coefficient a n. This is q. A naught is p. A naught is our constant term. P is our constant term, the factors of the constant term. Q is the factors of the leading coefficient, the number in front of the variable with the highest exponent. Okay? Rational zero test. So constant term over the factors of the leading coefficient. So when we look at this here, the first thing I would do, especially if you're not used to this, is list out P and Q, factors of P and Q, factors of P and Q. So P is the factors of the constant term. The constant term here is 6. We don't worry about the negative. P over Q. Well, our number is 6. Yes? Back up. So the number is 6, but the factors are 1 and 6, 2 and 3. 1. Only factors. We list out the factors. Okay? And this is going to take 2 days because I'm about to make one here. We have P over Q. So let's start 1 and 1. So we have plus or minus 1. 2 over 1 is plus or minus. 3 over 1 is plus or minus. Plus or minus. So these are our rational zeros. 1 plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. So those are our rational zeros. And that's it, okay? So any questions on this so far? All right. Now, what we're going to do is we're going to find them. We're going to find these zeros. We're going to do synthetic division. I'm going to do synthetic division. So we have all of our terms, yes? 4, 3, 2, 1, constant. So x to the fourth would be 1. Then we'd have 1. Okay. I'm going to start off with positive 1, because that's one of the possible ones, yes? 1 times 1 is? Negative 1 plus 1 is? 1 times 0. 1 plus 0. 1 times 1. Negative 2. 2. Negative 8. Did that work? Nope. Okay. Yep. Now I'm going to go to negative 1. Negative 1 times 1 is? Negative 2. Negative 2 times negative 1 is? 2 plus 1 is 3. Negative 1 times 3 is, which would give me 6, which is, that one worked. Negative 1 is 0. Let's try it again. Because there's nothing that says that I can't have it twice. So we're going to do it again. Negative 1 times 1. Negative 2 plus negative 1 is 3. 6. Negative. Okay. 1 twice. So we can go 2. Positive 2. Erase that. Positive 2. 1 times 2. Negative 2 plus 2 is 0. 3. 6. 0. Hey, that worked. And I normally continue to do this until we get a quadratic. Now, the reason I said that was constant term x. So really what I have is x squared plus 3 equals, now I can solve. So x squared equals negative 3. X is equal to plus or minus what? I squared of 3. So the textbook, I believe it'll write it as square root of 3i, but I like writing the I first just so it doesn't somehow magically migrate inside the root. Negative 1 and 2. These are our 4 roots, yes? And what was the degree? It was degree. How many solutions do we have? How many should we have? 4. We're done. That's it. Questions on this here? Would y'all say that was a pretty long and arduous process to find each one of those zeros going one at a time, yes? I mean, it wasn't too bad. 1, 2, 3, 6. So we had 8 because we had 4 positive and negative. We had 8 solutions. So it wasn't too hard to find those there. When leading coefficient polynomial is not 1, the list of possible rational zeros can increase dramatically. In such cases, the search can be shortened in several ways. One, a programmable calculator can be used to speed this up. A graph drawn either by hand or graphically can, or the intermediate value theorem can also help. So any of these here can help find it. Or we can use synthetic division, can be used to test the rational zeros. I will add a 5th one, or kind of mentioned in the first one, using a calculator to speed this up, and we'll see that sped up here in a second. And this here, because so far they really haven't, I mean, 8 numbers isn't that bad. Doing synthetic division, doing one after the other. It's not bad. It's not great. It's not bad. This here. So Q, 1 and 84. 2 and 42. 42. 3 works. 2 would be 6, which gives us 24, which would be 8. And you can try that in the calculator, just make sure. 4 and 21. 5 doesn't work, but 6 does. 6 will work. 6 and, what would that be? Yep. 6 and 14. How about 7? 7 and 12. 8 doesn't work. How about 9? No. 10. We're done. 12, 14, 21, and I'll leave the rest of these down here because we're not going to have space. And that was our P values. Q, 1 and, I'm going to drop this down, 120. 2 and 60. 3 and 4 and 30. 5 works. 6 and 20. 7 I don't think works. 8, I just have to do 8. 120 divided by 8. 9 we'll have to just check, which I don't think it works. Nope. 10 does. 12 and 11 doesn't, so that is
way too many numbers.
well, we haven't even reached the number of possibilities yet. Because again, the number of possibilities is P over Q. Now with this here, since we're all, well, I always start with the value of Q at 1, because I move Q up as we go. So we're dividing everything by 1, so it's just plus or minus 1, plus or minus 2, plus or minus 3, 6, 7, 14, 21, 28, 21, 28, 42, and 84. Now we move on to 2. So 1/2 is always going to be there. 2 divided by 2 is, hey John, then we have 3/2. 4 divided by 2 is 2. 6 divided by 2 is 3. We have it. 7/2, because that doesn't simplify and we don't have it. 14. 21, we do. 28, we don't need. 42, we don't need. 84 over 2, we don't need. We have those. 3. 1/3. 2/3. 3/3 we don't need. But we do need 4/3. 6/3, we have it because that's 2, but we do need 7/3. 12 divided by 3 is 4. 14 doesn't divide by 3. 21 does divide by 3. 7. 28 divides by, no it doesn't. Very tempted to say it does, but it doesn't. 42 does. 84 does. 42 divided by 3 would be 14. We have it. 84 divided by 3 would be 28. And we have it. So we're good with 3. 4, so we need 1/4. 2/4 is 1/2. 3/4 we need 1. 5/4. 6/4 would reduce to 3/2. So we have 6/4. So 5/4 doesn't reduce. Oh, thank you. Thank you. I see what you're saying now. Yes, I was looking at the wrong one. So 3/4, 4/4 is 1. 6/4 we don't need. 7/4 we do need. Don't need 12. 14/4 have a common factor of 2, which reduces to 7 halves, which we have. 21 fourths doesn't reduce because there's not a common factor of 2. 28 fourths reduces to 7. 32 fourths reduces to, because there's a common factor of 2, which would be 21 over 2. 21 halves, which we do have. 48 over 4 does reduce, so we're good with 4s. 5.
Wait, no, it should be 5. It should be
Yep.
6.
No.
Yeah, you're right.
So we're in the denominator, so we're switching to a new one. So we're good. 1/5.
I'm just like
1/5. 2/5. 3/5. 4/5. 6/5. 7/5. 12/5. 14/5. 21/5. 28/5. 42/5 and 84/5.
not even halfway to it.
8, 10, 12, 15, 20, 24, 30, 40, 120.
There we go.
1, 2, 3, 4, 6, 7, 12, 14, 21, and 84. So we're moving on to 6. I didn't write it on. One 6 is going to be there. Pretty much 1's going to show up in every single one.
2/3 is already there.
So 2 6 would be 1/3, which is there. 3 6 is there because they have common factors. 4 6 would be 2/3. 6 6 is 1. 6 we need. 12 6 is 14 6 is 7/3, which we have. 21 6 is just 21. Actually, yes, 7 halves, because they both have a common factor of 3. 3 times 7, 2 times 3. 28 would reduce, which would be 14/3. So I just plug it in, just check. There's nothing wrong with checking. 28 or 21 6. No, we did 21 6. 28 over 6.
14/3.
So we have that. 42 over 6 is 8, I believe.
42.
Actually 7. That's 7 that reduces wholly. 84 will reduce all the way. So we're done with 6. Now we have 1/8. 2/8 is 1/4. But we don't have 3/8. 4/8 is a half. 6/8 is 3/4. Is 3/4. We don't have 7/8. 12/8 should reduce. 14/8 should reduce. But 21/8 will not, because 21 is 3 and 7. 3 and 7 aren't factors. There's no common factors with 8. The rest of them should. They should reduce because they have at least a common factor of 2. We should have some common factors. So 8 is done. 10. 1/10. 2/10 is 1/5. 3/10. We don't need 4/10. We don't need 6/10. 12/10 would reduce. There's a common factor of 2. 14 would, 21 wouldn't. 28, 42, and 84 will all reduce down to something that we should have. Because, again, 2 and 5 are the only factors, so if it doesn't have a common factor of 2 or 5, so now 12, plus or minus 1/12. 2/12 would be 1/6. 3/12 would be 1/4. 4/12 would be 1/3. 6/12 would be a half. We don't have 12ths. 12/12 is 1. 12 over 14 would reduce. 21 over 12 will. It has a common factor of 3. 28, 42, and 84 should, because we have 2. 1/15. 2 15s won't reduce. 3 will. 4 won't. 6 will. Both have 3. 12 will. 14 won't. 21 will, because again, it's almost any that have a 3, because it's reducing 15 down to 5. We had everything with 5. 28 is 4 times, yeah, just type it in, just let's make sure. 28 over 15 probably won't reduce, because that would be 7 times 4. Yep, nope. $42 will and 84 will, because they both have 3. 20. 1/20. 2/20 will reduce. 3/20 will not. 4/20 will. 6/20 would be 3/10. 7/20 won't. 12/20 will reduce. 14/20 should reduce. 21/20 will not. 28, 42, and 84 both have at least common factor 2. They should reduce to something we already have. 1/24. 24 has 2, 4, and 3. So 1/24, 2 over 24 would be 1/12. We have 12s. 3/24 would be 1/8. We have 8s. 4/24 would be 1/6. 6/24 would be 1/4. 7/24 would be 1. No, it won't. 7/24. I was very tempted to say 1/3. That's 1/12. That'd been 7/21. 12/24 would be 1/2. 14/24 would be 7/12, which we do have. 21 over 24 would reduce because they both have a common factor of 3. 7/8, which we do have 7/8 up here. So that was 21. 28. Yep, that's ones we're going to have to write because it doesn't have as much as we would like it to. 24 and 42 and 84, and those reduce. 30. 2 over 30 is 1/15. 3 over 30 is 1/10. 4 over 30 would reduce. It's 2/15. 6 over 30 would be 1/6. 7 over 30 would not. 12 over 30 would reduce because it both have a common factor of at least 2. Actually, 2 and 3. No, not 2 and 3. Because 2 would be 6/15, which we do have. Or 4/10. 14 would reduce. 21 will reduce. 28 will reduce because 2. 20, 42, and 84 will all reduce. All of those will reduce because they all share a common factor of either 2 or 3 in most of them except for 2. 40. So 1/40th. So we have that. 2/40ths would reduce. 3/40ths won't. 4/40ths will. 6/40ths will. 7/40ths will not. 12, 14, 21. And the rest of them will. 2/60ths will. 3/60ths will. 4/60ths will. 6/60ths is 1/10. 7/60ths will not. 12, 14, 21 would reduce because it has a common factor of 3. 28, 42, 84. 28 over 60. Yes, it will. It has a common factor of 2. We're good. 120, the final stretch right here. 1/20th won't. 2/20ths will. 3 1/20ths will because they have a common factor of 3. 4 1/20ths will. Common factor of 4. 6 will. 7 will not. 12 will. 14 2. 21 will because there's 3. 28 will. 42 will. 84. 28 2 2. So we have all of these here. So when it said they increase exponentially, they legitimately increase exponentially. Yes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60. And that was it. 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 146. Yep. So, ish. I probably missed 1 or 2. But this is the number of possible, or the number of possible, these are rational zeros, possible rational zeros. And really, graphing it will help us figure out what they are. Because not all of these work.